So let me begin with a generalization. An extension of what we did on Wednesday. So let's begin with polar regions, not rectangles. So let's suppose that we have defined the XY plane. The XY plane is a backdrop to everything we are doing, or the XYZ space. Okay. Now we are going to look at two rays. Okay. Coming out of the region. This angle here is alpha. Let me make it a little bit bigger. I make it too small on Wednesday because there were so many things on it. And this is the bigger angle. Okay. This smaller angle is alpha. And the larger angle here is theta. Okay. That's basically what I put down on Wednesday. The larger angle is theta, the smaller one, alpha. And then I have a curve. Well, not part of a circle. So it's quite an arbitrary curve. And then another. Which I can refer to as the polar curves. So this one here is given by this. So the radius depends on the angle theta. And this is the first one, so I call it R1 of theta. And the other one, still a lot of stuff in it, is given by R, expressed as R2 theta. And this is the region we are looking at.
Sir?
Yeah.
So just to clarify, the smaller angle is theta and the bigger one is beta, right?
The smaller angle is alpha, the bigger
Alpha?
is beta.
Okay, okay, so the larger one's theta, okay.
Okay?
All right, thank you.
Okay. Theta is somewhere inside this, but I am not going to put down any more letters. Otherwise, it's very messy. We don't need it for the time being. So this is the region R. So R it's hard to write on this because it's moving all the time. So capital R is the set of all polar coordinates in which R is between R1 of theta and R2 of theta. So it's a little bit more general. And the one again is very messy. Let me write it more properly by holding the board. It's the set of all polar coordinates in which R1 theta is less than or equal to R, and R is less than or equal to R2 theta. And theta is between alpha and beta. Okay, that's the region. So recall capital R here, a polar region, a region in polar coordinates. And the graph of the two equations also have these. And people call these the polar curves. Okay. All right. So much for the terminology. If this were taught in 1310, then I need not introduce this here. All right. So let's assume that we have a function. And the function is continuous. Continuous on where? Well, on R. On a polar region R. Okay. This one. Then the question is the same old question. What's going to be the double integral? Of the function f with respect to a. Okay. All right. Now, if you use this diagram, I can give you the formula in exactly the same form. Well, not exactly the same form. In a form similar to the one on Wednesday. Okay. So this time, let me clear this a little bit. So this is the XY plane. We have a ray coming out of the origin. And another ray. Now, the smaller angle, this time, how am I going to draw it? Okay, this is alpha. bigger angle. The bigger one is theta. Again, how am I going to mark it? Let me mark it like this. No matter where I mark it, it's confusing to you. If I mark it here, you may think that it's only this part. If I mark it here, you may think that it's the subtended angle. But in fact, it's the whole angle. Okay? That's important. The angle with the x-axis. And this is the polar region. Okay. This is R2 of theta. And this one here is R1 of theta. And we are interested in finding the integral. On the region R of the function f. Now, the way to do it, again, is by picking a point inside the region, right? And then I am going to look at the ray. From the origin to that point. Okay. Now, let's suppose that the ray passing through this given point in the region is theta. This is the theta. Okay, this is theta. In other words, theta is bigger than alpha. But less than beta. Okay. So where should I put it? Let me put it here. So I fix a theta less than beta, but bigger than alpha. Then we are going to look at the range of the ray. okay, of the ray making the angle theta with the x-axis? Well, actually this point goes from this point to that point. So we are interested in knowing what this is equal to. So if theta is between alpha and beta, then what happens to R? So R will be larger than R1 theta. We are setting the limits. And it will go to from R1 theta to R2 theta. Right? So that's it. So this tells us what? Well, we are going to get the integral by rotating this line or this segment of the line so that the whole thing would sweep out the whole region. So in other words, this is the way to set up integrals. Okay. So this double integral is equal to the following. So we are going to end up with f of x, which is r cosine theta, and y, which is r sine theta, with respect to dA, which we have calculated to be dr d theta. Now we have to set the limits of integration. So theta belongs to the second integration, the outer integration. So this is from alpha to beta. And then once you have a specific theta, you have to look at dr or r. What's the range for r? So it's R1 theta to R2 theta. So this is very similar to Wednesday's work. But on Wednesday, we have a polar rectangle. And then the limits for the R integration are fixed numbers, if you still remember, from A to B, if I remember correctly. Okay, so much for this. Let's look at an example. And these examples are interesting because the curves in polar coordinates usually give us very nice regions, beautiful regions. Study a lot in algebraic geometry. When I was arguing with my colleagues about not introducing polar coordinates, and then I said, well, then students would miss out a lot of advanced mathematics. And you know what they answered? They said that, well, if they want to study those objects, they can come back to learn polar coordinates. This is not the way things should be taught anyway. You want to attract students to a certain field by preparing them first. That's the important thing. Okay, let's look at an example. And you can see that it's not that trivial. I have given you some exercises in this direction. Not exercise, example. Now let's try to find the area. Of the region. Bounded by the following polar equation or polar curve. Let's take the following polar equation. So R is a function of theta. So I simply take a simple one, cosine of 2 theta. Okay. Now, just this single equation doesn't give you a curve. So we have to specify the angle and the radius. So the angle is between pi/4 and minus pi/4. And what about R? It's just like X and Y. You have to specify them. So R, let's say, is bigger than or equal to 0. Well, I have told you that R cannot be negative. But when R is equal to 0, what do you get? Can anybody guess?
0 radius.
So what do you get?
Is that the origin?
That's the origin. That's good. Okay, it's a point at the origin. Okay. And then this is less than or equal to cosine of 2 theta. Okay, so we have one equation, two equations, and a third equation.
Hi, Professor.
Yeah.
Y is not R is not less or equal to 1, but less or equal to cosine 2 theta.
Yeah. Not 1. If it's 1, it's 2 is. Okay.
Okay.
All right. Well, maybe not 2 is. All right. Well, let's try to find the region first. This is the part that should be done in 1310. So solution. Did I put down 1 in the notes? No. So first of all, we have to look at the region. I ignore X and Y now. Now I want to find the region. Well, the region has angle between minus pi/4 and pi/4. Pi/4 is 45 degrees. So the region should be inside this portion of the right half plane, correct? Yeah, this is pi by 4. This is minus pi by 4. Now, again, the technique is by plotting a few points. Well, we have the origin, r equal to 0, right? R equal to 0 is a point in the curve of the region, or is in the region. And now I am going to look at pi by 4. What is it? What is R when the angle is pi by 4?
R is a 0.
Theta or no?
What's R?
Yeah.
Cosine to
Sir, I have a question.
yeah.
So if the angle is negative pi over 4, would that like that wouldn't change r, right? Because r is just the hypotenuse.
Mhm.
Yeah. So r wouldn't change even if the angle is negative pi over 4. Okay.
Okay. It's also 0. So when theta is minus pi by 4, it's also 0. And then you may say, oh, well, it's just a point. But there are some other values of theta.
Oh, we can take theta 0 and the pi over 8, plus minus pi over 8.
Theta to be equal to 0. What is R?
1.
1. Because theta equal to 0 is also in between. And there are some other points. But once you come to this point, you already have some intuition about the origin. So it starts with 0. The curve is continuous, right? And then it keeps going and go back to the origin again. So this is the origin. It's a leaf. Okay. And it's not a function. It's not y equal to f of x, which is a function. Because if you take any point in the x-axis, you have two values associated with it. Okay. So this is the origin. Okay. And the origin is hit 3 times. So it's not too difficult to draw this kind of polar regions. Now, I want to find the area. And at the end of Wednesday's lecture, there were a lot of questions about this, volumes, areas, and so on. Now, how to find the area of this one? Using a double integral. What should be the function being asked? You want to get the area. So what function should be used? Okay, you don't know this. If you want to find the length of an interval, AB, what should be the function you are integrating?
F of x.
I know, but that's too general. What specific function?
Should it be y equals a constant? Some arbitrary constant?
I want to find the length of AB. So what should be the function? Take one, right? When you integrate one, you get x, and then you evaluate at b, you evaluate at a, and subtract. You get b minus a. That's the length. The same thing here. You are going to integrate all those little parasites. That's the terminology I used. And then you add them up, and then you get the whole leaves. Right? So what should this be? It's also 1. Okay? Now, in order to integrate 1, we get the area, but what method should we use? Well, in this case, of course, polar coordinates. I don't see any other way of doing this. So I integrate from minus pi by 4 between minus pi by 4 and pi by 4. People usually skip the 1. Okay? It's understood. And then what about R? Take any angle theta. Okay, take any angle theta. Between minus pi/4 and pi/4. Well, this is theta. Then all would go from 0 to this point. But this point is cosine 2 theta. Because the curve is cosine 2 theta. So you don't go to 1. You don't just go there. You go there. Right? So it's from 0 to cosine 2 theta. And then R dr d theta. Okay? So this is what we are going to get. Now, for simple integrals, I expect you to be able to compute. So the area is equal to the integral from minus pi/4 to pi/4. And then it's easy to integrate with respect to R. It's R squared over 2. From 0 to cosine 2 theta. And then d theta. Right? And then I am going to put R equal cosine 2 theta. I can take 1/2 out. And then I have cosine squared. Two theta. And then I integrate with respect to theta. Now, this is an even function. And you integrate this on a symmetric interval. Or actually, you don't even have to care. Then it's the same as integrating on 1/2 of the interval. But then you have to multiply it by 2, which would cancel this one. But how do you integrate this? Well, you use the so-called half angle formula or double integral double angle phi. These kind of things are very important for partial differential equations. Now, what is this? Cosine square 2 theta would be 1/2. One plus or minus.
Plus 1 plus cosine 4 theta.
Yeah, because it's cosine
2 times 2 theta.
Yeah. Plus cosine 4 theta. That is very easy to compute this. Well, if you don't believe it, you can actually expand this. You can write this as cosine 2 theta plus 2 theta. Okay? And then you have cosine, cosine, minus sine and sine. That's why it's plus here.
Professor, don't erase, please. Oh.
Oh, I just.
That's okay. In the last class, I asked you about the line which you wanted to erase, the middle part. Therefore, the reason is integral angle alpha to angle beta 1/2 r squared theta. Here we have r cosine 2 theta, right? So we can directly come here, well, without using double integral.
What is it? I don't know. You have to use the half angle formula.
No. Before
Or
half
you
angle
use
formula.
Okay? Let me erase this. Let me finish this one first before you ask. So I am going to have 1/2. Well, this one is easy to integrate. Is theta. This one is also easy to integrate. Sine 4 theta, sine of 4 theta over 4. And then you evaluate at 0 and pi by 4. Okay, the area is this. And then you are going to put pi by 4 inside. So I have pi by 8. And then I have pi by 4 inside, and that's 0. If you put 0 inside, you get 0. So that's the area. Actually, the answer in my notes is not correct. Okay, so it should be pi by 8. Okay. I see why it's not correct. Because I put down 1/2 in the line, the 4th line from the bottom, it should be a 2. Yeah. Okay, this should be a 2. Okay, so make the correction for me. Okay, so what's your question again? How can you integrate cosine square right away?
I wrote in the chatting.
Pardon me?
Yeah, when we use the small, very small sector as a unit increment of the reason, we can find the area of the reason using single integral with respect to angle only.
Wow, but I need a double integral to do it.
So is there any specific reason we have to use a double integral here?
Yeah, because we are learning double integrals in polar coordinates. Okay.
I see. I see.
Yeah, okay.
Yeah, it's clear. Yeah.
I think that's a good answer.
Sir?
Yeah.
Can you explain how you got cos squared 2 theta to equal 1/2 bracket 1 plus cos 4 theta?
Well, that's what I said. So of course, none of it is memory. Now I can write cosine 2 theta plus 2 theta, right?
Yeah.
And then you use the fact that cosine of A plus B is cosine A cosine B minus sine A sine B. So I have cosine square 2 theta minus sine square 2 theta. 1 minus sine square 2 theta is cosine square 2 theta. So I have 2 cosine square, but I have half and cancel.
Okay, thanks, sir.
But remember to correct my notes, okay? From the bottom, in the line from the 4th line from the bottom, the 1/2 there should be 2. There was a 2 here.
Professor?
Yes.
In our next test, will we have more time than we were given last time? Because these are longer problems and they take more steps to resolve. So I'm wondering about the next test.
I don't understand you.
Will we be given more time to solve, to complete the next test?
I think it's still 15 minutes.
Oh, God.
Okay.
Okay, thank you.
Hi, Professor.
Actually, you get more than 15 minutes because I gave you quite a lot of time in uploading.
Hi,
The question is
Professor.
so much longer, though.
I don't think it's long. Anyway.
Well, it depends on how many questions we have, but doing the double integral, especially for polar coordinates, I have been practicing, and these take at least 10 minutes to get through one of them.
Yeah, the more you practice, the more efficient you are. So that's the point. You still have a few more weeks before the test.
Okay.
And I will think about making the integrals easy to compute.
Like if you give us like the bounds and we don't have to find the bounds for the integral?
No, that's basically what I need to test.
Oh my God. I thought you had just given us the bounds.
You get the integral right.
Oh.
And if you cannot compute the integral, I am not that upset. But the whole problem is to set up the integral.
Okay, all right.
Does it make sense?
It does make sense.
Yeah, okay.
Thank you, Professor.
Hi, Professor.
Yeah.
I want to ask y is integral, a double integral 1 for the area.
What's that again?
Y the area equals to double integral 1 dA.
I think I explained this using first year calculus. If you are given an interval, AB, let's say both are positive. How do you find the length of this interval? So you use an integral. This is something like dA. So the function is 1. When you integrate 1, you get x. And then you put x equal b, you put x equal a, and subtract, you get b minus a. That's the length. Okay. All right. For double integral, let's take an arbitrary region. Oh, it doesn't even have to be type 1. All regions have an area. And if you want to use a double integral to find the area of the region, pick a point inside. Okay? And then you blow it up a little bit, not too much. So let's say you get a small rectangle, a small region. It doesn't have to be a rectangle. Okay? This small region is very, very close to the point. So you might as well look at this small region. And then we calculate the area for this. That's the area. Now, if you add up all these areas at every point of the region, then you get the area of the region, right? Let the point move all over the region. It carries with it this little bubble.
So, Prof, I have a question.
Yeah.
So
finish this one first.
Okay. Sorry.
Okay. So you are going to let this go over the whole thing. So what is it? This is the integral. This means adding over the region R. Integration is just like addition. Continuous addition. That should be emphasized even in a proof-based course. So this is one. But usually if you have one here, you skip it. And this is the area of for any coordinates. Later on, when we want to find volumes, it's the same thing in triple integral. Okay. So what's the another question?
So Prof, so dA is just like a small little section of R, right?
Exactly. No. The area of a very small section at a given point.
Okay. So it's the area of the little small section. Okay.
Yeah. Okay.
And when it's added up, that's the entire area of R.
And then you let this point go.
Yeah. Okay.
Then you add up all these areas.
Okay.
And that's the total area.
Okay.
Well, sometimes explanations like this are better than using partitions and so on.
All right, thanks, sir. That was very clear.
Okay, good. This is actually the best method to introduce integration. So, anything else?
Sarah, we were talking about the test earlier, and would we be allowed to use websites like an online integral calculator on the test?
Yeah, I think I mentioned it in the instructions.
Okay, thank you.
Yeah, I allowed everything except consultation with individuals.
So sir, so say we do use the online integral calculator, we still have to show like all the steps, right?
For simple, yeah. For example, last time I put down cosecant cube. You see how difficult it is.
Yeah.
Yeah. But then these are tabulated, even in a textbook.
Huh, okay.
Yeah.
So we can use a online integral calculator, and if it's very like complex, we don't have to show all the steps.
If they are very complex, you don't have to show all the steps.
Okay, cool.
Okay, let's put down. I need the answer. I emphasize on answers. Well, not emphasize. I give credit to answers. Okay.
All right, thanks, sir.
But the question, why do people integrate one to get area, is exactly that picture. That dA is the area, very small area at any given point. And then you add up all these little areas, then you get the whole area.
Sir, like in our test answers, should we like say that we use the online integral calculator?
Yeah, maybe it's a good idea to say it.
Okay.
By,
so from using an online integral calculator, I got this.
Yeah.
Okay.
Okay. Only for very complicated ones, but
yeah,
we get very complicated ones.
Yeah, like if it's like an integral of like 1, is just very easy. X minus A. Yeah.
Well, cosine, sine, and so on, they are very easy.
Yeah.
Okay. But it seems to me that this class doesn't know integration very well That's the impression I got. So, any further questions? Some students even ask me, well, are there a lot of integration in this course? I said, yes, but I won't give you very complicated integrals to compute. So any further questions?
No.
No. Okay, good. Okay, then.
All right, thank you, sir. Have a good day.
See you on Monday.